Okay, so the topic of this lecture is going to be, as I said earlier, normalizing flows, which are going to be a new type of generative model. We're gonna be defining precisely what normalizing flows are at the end of the lecture, but first I'd like to motivate why they're needed, why we're going to look at them, and then we're also going to see we're going to review some facts from calculus. We're going to be in particular looking at this change of variables formula in probability and calculus. And this change of variables formula will be the mathematical tool that will be needed to define what normalizing flows are. So that's the plan for the lecture. To introduce and motivate normalizing flows, let me first start with a quick recap of the two types of generative models that we've seen in the last 2 weeks. Remember that we first started with autoregressive models. And these models can be essentially defined by the following formula, which is the chain rule of probability. They start with this formula, and the key insight of an autoregressive model is that you can look at these conditionals, you can take these conditionals and you can parameterize them using expressive neural networks. And these neural networks predict the next element of the object. So for example, the next pixel in an image based on the previous pixels. And using these models, you can now generate images or audio or any kind of data, one element at a time or one pixel at a time. And there's two main ways of specifying what this conditional is. One technique that we saw earlier, which is not an instance of deep generative modeling, but it's a classical and important technique in machine learning, that's using conditional independence. These kinds of models are called Bayesian networks. But the more modern way of doing it, and what we're looking at in this course, is using neural networks for parameterizing these conditionals. And that leads to models like WaveNet or Pixel CNN. And there's also a few older models that we have seen. So those are autoregressive models. Autoregressive models have a lot of advantages. First of all, it's easy to evaluate their likelihoods, which is going to be actually not obvious for most generative modeling families. So this property is actually it's actually somewhat unique to autoregressive models, or at least it's much easier to do this in autoregressive models than in other families, where we have to do a lot of more clever things. But it's really straightforward in an autoregressive model. And because it's easy to evaluate the likelihood, well, it's also tractable to train using maximum likelihood learning. Now, on the other hand, autoregressive models also have some disadvantages. First of all, we have to choose some kind of ordering, which is not something that's really natural. It introduces an unnecessary modeling assumption or bias. So why would there be any ordering over the pixels? Why would we be going left to right as opposed to top to bottom? These things are a little bit unnatural. So this is more of a conceptual shortcoming. A slightly more important shortcoming is that because these models are autoregressive, we can only generate from these models one pixel at a time or one element at a time. So generation is sequential, and oftentimes this is going to be slow. And finally, the third and maybe one of the biggest disadvantages of autoregressive models is that there aren't any latent variables in these models. So there's no natural way of doing unsupervised representation learning, which is a key task in generative modeling. And to address this last limitation, we looked in the last two lectures. So last week, we looked at latent variable models, which are a set of models in which we have introduced this additional variable z, that's our latent variable. And this variable z, once we have learned the model, it can be used to identify interesting hidden factors of variation in the data. So for example, if we have a data set of faces, we might hope that Z will cluster similar faces. So similar faces will be mapped to similar Z, and therefore, by inspecting the clusters in latent space, we might be able to discover groups of similar individuals. So for example, individuals that have the similar gender or similar skin color or similar age, we might be able to discover all of these latent attributes from data in an unsupervised way by inspecting the variables Z. That's our main hope. And the most famous model, the most well-known type of latent variable model, and the one that we have derived at the end of the last lecture, is the variational autoencoder model, which is essentially shown here in this figure. And we looked at this figure in a lot of detail in the previous, at the end of the last lecture. Okay, so that's what latent variable models are. And they also have pros and cons. So the pros and cons are that we can, as I said, perform unsupervised representation learning. It's also very fast to sample from them. We can do what's called ancestral sampling, where we first sample a Z and then we sample an X given Z. And that's non-autoregressive, so sampling is fast. The main problem is that computing exact log likelihoods becomes intractable. And the reason why it's intractable is that computing this posterior distribution P of Z given X is hard. We have to deal with complicated integrals like the one you see here, and that makes things much more complicated. And to deal with this, we derived in the last two lectures this mathematical machinery called variational inference. And variational inference allows us to perform approximations of this posterior. So instead of computing the exact P of Z given X, we compute an approximate Q of Z given X and use that to do approximate inference and to approximate log likelihood learning. In practice, it can still work quite well, but it's still fundamentally an approximation. And so if ultimately your goal is to perform density estimation for outlier detection, for example, then latent variable models are not the best ones. You would probably want to use something like an autoregressive model instead. Okay. But as you can imagine, this raises the question, is there a way to have latent variable models that combine the best of both worlds? And by that, I mean they have latent variables and they also have tractable likelihoods. So we would like to combine the advantages of autoregressive models and latent variable models. Can we do this? Well, it turns out that the answer is yes. And that's what normalizing flows are. They're going to be a class of latent variable models that combines both latent variables and exact posterior inference and exact log likelihood estimation, at least in theory. There's going to be a lot of practical complications, but at least in theory, this is going to be a class of models that will combine the benefits of both autoregressive and latent variable models. Okay, so that was my high-level motivation for why we need normalizing flows. Let's now look at what normalizing flows are. And as I said earlier, in order to do this, we're going to have to use this tool from calculus and probability theory called the change of variables formula. I will explain to you in a second why we need it. So the next few slides are going to be a bit of a calculus review, but I think understanding this part of calculus will be really useful in order to define and get these models to, in order to define and understand these models. That's the plan. Okay, so what is going to be our overall strategy for defining normalizing flows? Again, we're looking for a tractable latent variable model with, so a latent variable model that's tractable in the sense that it has this log density that we can compute, and we can also perform latent variable inference. But let's just say for now we want an expressive model family that has a tractable log density. How can we do this? Well, there's many simple distributions in probability that have this property, right? If we look at a Gaussian or if we look at a uniform distribution, we can easily compute their density. These are the types of distributions where pretty much any task is straightforward, very tractable. Unfortunately, Gaussian distributions by themselves are too simple for us. We can't really fit a Gaussian to a complex data set and have a good model. So they're not sufficiently expressive. The key strategy used in normalizing flows is to start with simple distributions. So we start with something which is simple, could be like a Gaussian or a uniform distribution. And then we're going to be mapping these distributions to complex distributions using a invertible change of variable transformation. So by that, I mean that we're going to define a distribution over complex data that will start with a Gaussian and then transform this Gaussian into a very complex multimodal probability distribution using an invertible mapping, which will shift around the densities. So for example, we could start with a simple Gaussian distribution, which looks like this, and then try to push some parts down, some parts up, and then try to make it something like this by pushing these things here, and then this thing might go here, right? So we can remap these distribution in interesting ways using a particular class of invertible transformations. So let's look at this idea first in a very, very simple example, which is going to be one where we have just a single latent variable z, here that's uniform in the interval between 0 to 2. And let's say we wanted to transform this variable in a really simple way. So first of all, let's look at what's the density of just z. Z is very simple, z is tractable. So what is the density of p of z of 1? So the density is 1/2, right? This is our density at 1/2, and then the area underneath the curve has to sum to 1. Okay, so it's 1/2. Now, let's say that we're going to transform z into another variable called x. And the transformation that we're going to use is going to be this one. We're going to define x as being 4 times z. Now, this is another random variable, and it has some density p of x. Okay, now, what will be the density of p of x? Okay, let's try one thing. Let's say that we have p of x. This is the quantity that we want to estimate, and let's just do a little bit of math. So we're looking at for the density of x at 4. So we're going to do some math here, and now we get for z given for z equals 4, which equals equals 1, and then p of z equals 1, and then 1/2. Okay, does anybody have any thoughts or reactions to this math? This is just, I'm only trying to compute the density evaluated at 4. So the density is a function. It's defined everywhere on the unit line. So before we had a density between 0 and 2, and that was 1/2, right? It was 1/2 here, and it was 0 everywhere. That was my previous density. Now I'm going to have another variable. And there's a 0, and then there's some density here that I would like to know what it is. And so now all I have done is I have told you there's this math that's trying to say that the density is going to be 0. So there's 0, there's something else, and then there's 4. And all that I'm saying is that p of the density evaluated at 4 equals also 1/2. That's all that this math is saying. Is there anything, is this correct or not? So this is not correct, of course. So it clearly can't be correct because So z is a uniform variable between 0 and 2. Therefore, 4 times z has to be a uniform variable between 0 and 8. And the density has to sum to 1, right? So it has to sum to 1. So it can only sum to 1 if it's 1 over 8. So this is clearly wrong. So why is it wrong? Well, it's wrong at this step here. This is not correct. This is not true. This is not true because here I'm using something which is a density, and I'm trying to equate it to something which looks like the probability of an event that is not comparable. So here on the left, I have something which looks like which is a density. On the right, I'm misusing P, and I'm using P as a probability measure, and a density and a measure are a density and a probability measure or probability distribution are two completely different. Well, they're two related but different things. So it's the first step here that is wrong. And at a high level, what happened here is that when we went from a distribution over 0 and 2, and we went to a distribution of 0 that's over the support from 0 to 8, this volume here, the area of support of the distribution has expanded. It has become larger. And therefore, but we still have only a unit of mass, right? Here we had a unit of mass that we have to remap to the other range. And this unit has to be preserved. We only have one unit here in black that we can map to the other interval, and therefore this unit has to be spread more thinly than it is on the left. So we have to account for changes in the size of the support of the distribution. And when there is more support, when the volume that supports the distribution increases, we have to scale down the magnitude of the density. Okay, that's a very key important fact to understand. And this is the problem that all of the math that we're going to do for normalizing flows will try to address. So I think it's important to think about this fact. If you're not convinced, please go over the slides again after the lecture, because this is the key technical challenge of normalizing flows. It's the fact that we have to adjust our density. When we transform one variable into another, we have to adjust the density of the new variable to account for the fact that the support of the distribution, which is this thing here, may have changed. Okay, so that's the difficulty in doing a change of variable transformation. How do we actually do a change of variable transformation? Well, we use the following formula. This is the change of variables formula from probability theory and calculus. And what it says here is that if we have a transformation from z to x that's given to us by a function f that is invertible and has an inverse f minus 1, and let's call this inverse h. So h is the inverse of f. Excuse me. H is the inverse of f. Then the correct formula for the density of x is the density of so we take x, we move from the density over x here to a density over z, but now we have to evaluate the density over z over the inverse of x, so over the z which was mapping to x. So this is what we did in the earlier example in the part that was by itself wrong. And in order to make it correct, we have to have this extra adjustment factor, which is the derivative of the inverse at x. So this is an adjustment factor that has to be applied when we perform these types of changes in density, change of variables, and we have to compute the density. So this is the correct formula. So let's just check if it works in our previous example. In the previous example, we said that this is our transformation. we wanted to compute this density. Here we have an instance of change of variables with a mapping. So f here is for x, therefore its inverse. The forward mapping f is 4 times z, therefore the inverse is x divided by 4, and therefore the probability of x is going to be the probability of the inverse of x. Here we divide by 4, so it's probability of z at 1 times this extra adjustment factor. And what is the derivative? It's simply 1/4. 1/2 times 1/4 is 1/8. And now this gives us the correct answer. Yeah. So again, this is the formula that we're going to be using. It's only in 1 dimension. We need to derive it in multiple dimensions, but this is the key formula that will be needed to define normalizing flows in a few slides. So again, what happened here is that we have expanded the support by 4. Therefore, we have to decrease the mass at each point by 4 in order to preserve the volume. There is also another way of looking at this change of variables formula, or there is a way of understanding what's going on using a little bit more math. Here is a little proof sketch of this formula. And what happens here is that we start with the density of z. Let's say we wanted to integrate z. If we were to perform a change of variables, well, here I can divide and subtract by dx, and then remapping the dx's, I get the following approximate. I get the following formula, and this part here, the dz over dx, is simply the derivative of h of x. And what's happening here is that you can think of the integral as being the limit of a sum over of infinitesimally small rectangles, dz. And so if I do a change of variables, I have to adjust by the ratio. If I switch from little rectangles or little blocks in z space to ones that are in the space of x's, I have to adjust by the change of volume. So this is the size of a block z, this is the size of a block x. I have to adjust the sum by the ratio of their volumes in order for this to hold. And the ratio of their volumes as the size of dz goes to 0, this ratio dz over dx will go to the derivative, right? So we're basically adjusting the size of these infinitesimal rectangles. That's an explanation for what the change of variables formula is doing. Okay, so everything that I showed you so far has been in 1 dimension, but we need to go further. We're going to use this formula to define distributions over very high dimensional x. X could be the vector that's representing an image or an audio signal. So x has to be very high dimensional. So we have to take this change of variables formula to multiple dimensions as well. In order to do this, we need to define a notion of volume in higher dimensions. And this notion of volume is given to us by a concept from linear algebra that we all know and love, called the determinant. So if you remember linear algebra, the determinant is a measure of volume in higher dimensional spaces. In particular, the determinant, or at least let's start in 2 dimensions. In 2 dimensions, the determinant of a parallelogram. So this red shape here is a parallelogram, okay, and its sides are given by 2 vectors. This is AB, and this vector here is CD. I can represent these two vectors in a matrix where I have AB being the first column, CD being the second column. And so now this matrix A is the linear transformation, which maps a unit interval into the parallelogram that's on this side. So it maps the green square into the red parallelogram. You can easily check that. And then the determinant of the matrix A is exactly the volume of the parallelogram. It is the volume of the range of this linear transformation, this linear function. I guess x equals a z is our two-dimensional mapping, and the volume or the area, because it's in two dimension, we're talking about the area of the support of the distribution of x is given to us again by the determinant of A. And you can check that this is true in one dimension, in two dimensions. You can check that this is true. We know that the formula of a determinant in two dimensions is just AD minus BC. And that is also the formula for the area of a parallelogram that we would learn in school, right? So here I have AB, I have CD, those are the coordinates. If you just if you just apply the formulas for the areas of various geometric forms like the parallelogram, in this case, the area should be AD minus BC, which is also exactly the definition of the determinant. So determinants are ways of measuring areas and volumes in higher spaces. It also works in 3 dimensions. So in 3 dimensions, our parallelogram looks like this. And the volume here, the volume is going to be the determinant of A, where A is now going to be a matrix A, B, C, right? Those are going to be my 3 columns of the matrix A. I take its determinant, and that gives me the volume of the parallelogram. And you can also check for fun if C happened to be collinear with either B or A, then the depth of the parallelogram would be 0, and we would have a volume of 0. And we know also that if A, B, and C are not linearly independent, if C is collinear in A and B, then this matrix A is not full rank, therefore it has a determinant of 0. So that intuition also matches. Okay, so these are volumes in 3D. And finally, what we ultimately want is a volume in ND, and a parallelogram in ND is called a parallelotope. And the volume of a parallelotope, which is again an extension of this parallelogram to n dimensions, is still given to us by the determinant of A. This is a fact, and hopefully you believe me. Hopefully you remember from calculus, and you also believe me after seeing the 2 low-dimensional examples I just gave you. Okay, so now we have a way of measuring volume in higher dimensions. Let's now use this to derive a change of variables formula for higher dimensions. First, let's again start with a uniform random vector Z and a linear mapping in a higher dimensional space, which is given to us by an invertible matrix A. A here is a matrix. We're performing a linear transformation of Z into X. So what would be the density of X? Well, we know that because Z is uniform, X also has to be uniform. So X is going to be uniform, but its support will be different. Its support will be not the hypercube. Its support will be the parallelotope that is defined by the matrix A. And so what is the volume of the parallelotope? Well, as I just told you earlier, its volume will be the determinant of A. Therefore, so what will be the magnitude of the uniform distribution for X? Can somebody tell me? It's going to be uniform with an adjustment factor of 1 over determinant of A. And so this here is going to be a Z. P of Z is uniform. Because it's uniform in the unit hypercube, this will simply equals 1. So this will equal 1 over the determinant of A. That's what I was looking for. So this is the formula for a linear transformation. So for a linear transformation, we can use the determinant. What if we have a nonlinear transformation? That's what we're ultimately interested in. Well, in that case, similarly to how we use the derivative to approximate a linearized change of volume in one dimension, we're going to use the Jacobian of F to approximate the linearized change of volume in F in multiple dimensions. That's the plan. What is the Jacobian? Let's remind ourselves what it is. Again, this is something you should remember from Calculus 3, but the Jacobian is the matrix of all the derivatives of a multivariate function F. So F here is a vector valued function. It takes as input a vector, and it also outputs a vector. So it's a mapping from an n-dimensional space to an m-dimensional space. And the generalization of a derivative to a vector valued function is called the Jacobian. It is simply the matrix. So J here, also written as, slightly abusing notation, written as partial F over partial X. That is going to be a matrix that's n-dimensional here and m-dimensional here. And each entry of the matrix is the partial derivative of one of these terms with respect to one of the input variables. This is a generalization of the gradient and the derivative. Now we're going to use the Jacobian to derive a multivariate change of variables formula. And so how are we going to do this? Well, remember I told you that in one dimension, when you think of the so you can think of the density as being the integrand. So when we a probability measure integrates the density over a volume in order to compute the probability of an event. Right? I remember that math where we had dy, where we had the dz over dx. So we can do something similar in higher dimensions as well, right? Except that our du and dv here are going to be small parallelotopes. And the adjustment factor for a parallelotope, so I guess you can, when we transform some kind of shape like this into another shape in a nonlinear way, we can approximate this by the transformation of a few small rectangles locally by a small linear transformation. And for sufficiently small rectangles, we can approximate this local transformation by a linearization of the original formula, and the ideal linearization is going to be given to us by the Jacobian. So, right, a first order approximation of what a nonlinear function is doing is to take a linearization of the input, and then for each little square here, we transform it into a different shape locally. We transform it into a little parallelotope. And the change of volume between this small region and this small region is going to be given to us by the determinant of the Jacobian at some point x prime, which is going to be within this region. That's going to be our approximation similarly to how we had, if you remember, we had the change of formula where we had dz over dx times dx, and I said we take, and I said this is an approximation to the change of volume locally around some point. Now I'm generalizing this to be the Jacobian, the determinant of the Jacobian. So now putting all of this together, this is the full formula for the change of variables formula. The full version of the change of variables formula, where we are in the general case. Here we have an f that's a vector valued function. It's an invertible mapping from Rn to Rn. So it takes a z and it spits out an x. Because it's invertible, I assume that it has an inverse f minus 1. And the correct formula for the density of x is going to be to first take this x here, map it to a z that's given to us by the inverse of f at x, and then we also apply this extra adjustment factor for the volume. And this gives us the correct change of variables formula in the general case. I'll make a few more observations about it. First of all, it's really important to note that x and z have to be continuous for this to work, and they have to have the same dimension. That's because, again, f has to be invertible. So they have to be continuous and have the same dimension. Otherwise, it being invertible doesn't make a lot of sense. So if x is in Rn, z has to be in Rn. Also, the other fact that we can use is that for any matrix, we have this property which holds, which means that we can equivalently take the -1 out of the formula. So it can be here, instead of being here, it is now here on the outside. And this is an equivalent way of writing the change of variables formula. Yeah, and again, these slides are all available on Canvas. So if you, you will have this formula in this exact slide available to you on Canvas. The most important, I guess my hope here is you understand at a high level the intuition for where this formula is coming from. And if you need a refresher, use these slides, or Calculus 3 is going to be, a Calculus 3 textbook is where these formulas tend to, I guess Calculus 3 plus probability would be the background that's needed to review this material. Okay, but for now, I have, up to now, I have done a lot of math, but ultimately what we have is a really useful tool. We have this really useful formula that we can now use to define normalizing flows. And I think you probably see where I'm going. I have two variables, z and x, and I have an invertible mapping between them, and I have a formula for the probability of x. I think you see where I'm going and how I'm going to use this next to derive the formula and to derive the normalizing flow model family. Okay, so then let's do exactly that. So the next step is going to be to use all of this machinery to derive normalizing flows. So what is going to be a normalizing flow? A normalizing flow is going to be a latent variable model over observed variable x and latent variable z. And the formula for x given z, well, first of all, P of z is going to be a simple model family. Similarly to a variational autoencoder, we can make P of z Gaussian or we can make it uniform, but P of z is simple. And P of x given z is going to be given to us by this mapping f sub theta, which is going to be invertible. So now, given z, x will be specified in a unique way by an invertible mapping f sub theta. And this f sub theta is going to be our model. That is the main component that will define our normalizing flow model. And again, I just want to reemphasize that this mapping is going to be a deterministic and invertible mapping that maps X to Z. So once we specify this invertible mapping, then we have a valid distribution over X. You could just imagine this distribution being formed. You can imagine sampling from this distribution by drawing a Z from the simple prior and then mapping an X given a Z. So we can at least sample from this distribution, right? For any F given Z, I can generate samples from X. They will have some form. If Z is going to be some kind of simple mapping, this one could be more complicated, but there is still some distribution over X that is defined by the reallocation of probability mass as specified by F. So this defines a valid probability. The question is, how do we learn this probability? And you can again see where I'm going. We have just derived tools that enable us to learn these models using maximum likelihood. So we want to use maximum likelihood here. And we have just derived a formula for the density of X when F is this invertible mapping that we're going to use. In particular, the formula for P of X is simply the result of the change of variables formula. So the density of X is given to us by the density of the inverse of X. So this here is, you can think of it as Z of X. That is the Z that uniquely maps to X, because F is invertible. For each X, there's a unique Z. Now I evaluate the density of this Z, and I apply this normalizing factor to account for the fact that we have a change of variables and the density has to be adjusted by the local change of volume. So this is just applying the change of variables formula. And now that we have this change of variables formula, we're going to be able to do learning. There's two important notes, two important observations that I want to make here. So this is really important. We can compute the marginal likelihood exactly. This quantity P of X was very hard to compute for normalizing for variational autoencoders. We had to derive a lot of complicated machinery based on variational inference to approximate P of X. In this kind of parameterization, using the change of variables formula, we get an exact formula for what P of X is. So this is really cool. Now, we still have to pay a price for this. The main price we have to pay is that XZ have to be continuous. So normalizing flows naturally work only over continuous variables. And they also have to have the same dimension. This can be a little bit problematic because if Z and X, well, X can be very large, can be very high dimensional. It looks like an image. And if Z is also very large and this mapping F that maps one to the other is invertible, then it can be a big function in the sense that it maps a big tensor to a big tensor. So it will in practice require more memory and more compute than just a formula that maps a small Z to a big X. So that's a practical consequence of the fact that X and Z have to have the same dimension.
Question.
Yeah.
The inverse may not always be tractable, right? Like computing the inverse may not always be tractable, right?
Yes, that's a really great point, and that's what I'm going to talk about next. Yes, so this is just for some F. I haven't told you what F is. And yes, in order for this machinery to work, we're going to have to choose our F carefully. So I mentioned that F might be mapping two high dimensional tensors to each other. So that is already potentially problematic. And even if you could Yeah. So it has to be, it's problematic to map a large set of numbers to another set of numbers in an invertible way, and many mappings will be invertible, but will be intractable. So we're going to have to be careful about that. And finally, one more subtle, well, I guess, can anybody see other problems with the fact that X and Z have to have the same dimension? Let's say we wanted to do unsupervised representation learning. What might be the issue with Z being of the same dimensionality as X?
You can't compress the dimensions to
Exactly. You're not compressing the dimension, which is also not great. You would hope that the set of latent factors are compact and small. You have high dimensional images, but they're explained by a small number of factors of variation, like skin color or age or gender. But here Z has to have the same dimension. In practice, you could still use you could still inspect Z and learn something interesting there, but it's not as satisfying as when you're learning a low dimensional Z. And the fact that you don't have this compression, it in some way can discourage the model from learning representations that would be ideal. The representation you might have from this model, there are reasons to think why they might not be as good as ones that would not assume, they won't be as good as ones that come from models that force Z to be small. That's another more subtle problem with normalizing flows. But again, exact latent variable inference and exact marginal likelihood learning are completely tractable now, assuming we can find a decent F. Right? So going back, oh, yes.
Another situation is the function also may not always be invertible, right? For example, you said we're going from a simple to a complex function, but the space of simple functions that we can map are basically normal or Gaussian, right? Again, because not all distributions may be like, not all distributions are invertible.
Yeah, well, so here we're not talking about inverting a distribution. We're talking about inverting this deterministic mapping.
Right.
But you're right that not all mappings will be invertible.
Okay.
But that's just something that we're going to assume. If it's not invertible, it's not a normalizing flow. But I think what you're saying, and that's absolutely correct, is that it's not completely trivial to find an invertible mapping. And that's another challenge of working with normalizing flows, right? So we need to construct this transformation. We need to construct the function f such that it is invertible. Otherwise, this is not a flow. We can't apply the change of variables formula. It also has to be sufficiently expressive to model the data that we're interested in modeling. If we have a distribution over images, then it has to be sufficiently expressive to map a Gaussian to the space of images, which is much more complex than just a Gaussian. So the parameterization f has to be very expressive. And finally, computing the inverse and the forward mapping and the inverse mapping has to be computationally tractable. And getting a good f is essentially the key challenge when working with a normalizing flow model. So in the previous in the previous set of models that we have seen, in particular in variational autoencoders, we don't have any restriction at all on what the generator and what the encoder can be. But because we don't have any restriction, we have to do a lot of more complicated probability theory to derive a good objective for them, to derive a learning objective and to approximate maximum likelihood learning. Here, we don't have that problem, but we have in some way shifted the difficulty to another part of the design space, which is how do you choose a neural net to parameterize your f while maintaining these three properties. So in this lecture, in the next lecture, we're going to see a few ways of constructing these f's, which have the properties that we want. But for now, I will give you one simple strategy that can be used to find an f that satisfies these three conditions. And the strategy is going to be essentially to combine small, simple, invertible mappings. What do I mean by that? So let's say we start with something like a Gaussian. So our first variable, we're going to start with a simple latent variable, z0. That's just z. That's the latent variable we had in our previous examples. Let's say it's Gaussian. And then we're going to try to form a sequence of latent variables using a composition of simple transformations, right? And here, when I have this circle, I mean the composition of functions. And each of these f's will be invertible and simple. Okay, and then this final Zm, that's effectively going to be x, right? So the final output of this sequence of M composition is going to be the object that I want to output. Why is this a good strategy? It's a good strategy because there's a simple way of computing the log likelihood and to apply the change of variables formula when our f is this composition. So when f is the composition, so we basically know that the determinant of a composition of functions equals the product of the determinants of each term here. So even though this function f can be, even though this function f can be very complex, it can have many layers here, it still has a simple formula for the determinant if each layer is simple. And in its change of variables formula, we're going to be multiplying the determinant of each f of m. And so if each f of m is simple, then this determinant will be simple as well. But the hope is that by composing many simple functions, just like we compose layers in a neural net, their composition can be expressive. That's the first strategy that we're going to use. Okay, what would be an example now of one of these simple invertible transformations? One example that I will show you comes from an early paper by Razenda and Mohammed in 2015. This is one of the early papers that popularized normalizing flows for generative modeling. And the particular formula that they used for a simple mapping is the following. So here we start with z, and then we add to z this extra term here. Okay, what is going on? What is this actually doing? This is a visualization of what applying this f recursively does to a uniform distribution. So we start with the uniform here, and then we apply one instance of this transformation. The result is a density which looks like this. And then if you apply it twice, it looks like this. And if you apply it 10 times, it now looks like this, which is a much more complex form than what we had earlier. Why does it have this form? You can, if you stare at the formula, you can see a little bit what's going on. So you see that there's a line here that's crossing the square. And so this line corresponds to this formula, which is also an equation for a hyperplane in, this is just the W transpose Z plus B. It's just the formula for a hyperplane that's defined by a normal vector W. So you can think of W as being this vector that defines this plane. And then depending on how far or how close we are from this plane, there is this adjustment factor that gets added to Z. And this is why you see this. This is why these densities look like they're the intersection of a number of lines or hyperplanes. So this is one intuition. This is one example of what type of simple mapping we could possibly use here. So we've seen here that we can get something that's reasonably expressive. Can can we now compute the determinant of this mapping? And the answer here is yes. I'm not going to derive this formula, but in the paper, Razenda and Mohammed work out the formula for the determinant. It can be, so this is the determinant that we have to compute, and we can apply a lemma called the matrix determinant lemma. This is something you can look up easily on Wikipedia. It is a formula that can be used to apply, it can be used to compute determinants of functions of this form. Now, there are some additional technicalities here. If you use any h, and if you don't have any restriction on the parameters, this mapping might become non-invertible. And so in practice, when the authors applied this type of model, they also restricted the parameters in a clever way to ensure that the mapping is always invertible. Okay. And so this type of model are called planar flows. It also works for other types of distributions. For example, if your base model is a Gaussian, then you get images which look like these. If it's uniform, then we get the type of density that you just saw. But the high-level idea here is that we can transform simple distributions into more complex ones by applying these simple transformations recursively. Okay, so now we have seen what is a normalizing flow, what is the general principle for learning and normalizing flow, which is maximum likelihood learning, where the likelihood is obtained using a change of variable formula. And we have also seen challenges in defining this in the invertible mapping of a normalizing flow, and at least one way of defining this mapping that achieves reasonable results in practice. Although I have to add that, so in the Razenda and Mohammed paper, they didn't use that normalizing flow model directly to generate images, but what they did is they combined it with within a VE type of model. So they used it to parameterize the prior of a VE and learn the prior. I have to add a caveat. So the model of Razenda and Mohammed, it doesn't generate images by itself, but it can be used as a component of other models. In particular, it can be used as a component of a variational autoencoder and makes that model more expressive. And we're going to see later normalizing flows that can generate images or more complex data like audio. They can generate that data directly. Okay, but that's going to be in the next lecture. For now, just a quick recap. Again, we talked about normalizing flows. So they're normalizing because we're applying the change of variables formula, and it has to give us a density which we need to normalize using the determinant of the Jacobian of f. And it's a flow because it smoothly maps a simple distribution into a more complex one. The main characteristics of flows is that we have to have a continuous x and z have to have the same dimension. And the key challenge is to define this f. One way in which this could be done is via a composition of functions f. All right. And learning in normalizing flows is done using maximum likelihood. So if we form the likelihood, that's log of p of x, we apply our change of variables formula to p of x, now products become logs, and this is the formula for the log likelihood that's derived from the change of variables formula. And the main challenge here will be to compute this term, the log determinant of the function f. And in order to maintain a tractable determinant, we have to use restricted classes for the function f, restricted families of functions f. For example, compositions of simple functions. Now, the benefits of normalizing flows, again, are exact likelihood evaluation. because this transformation x to z is invertible, we can apply the change of variables formula to get exact likelihood. We can also sample from these functions easily. We perform ancestral sampling, which means we sample from the prior and then we pass z to into f to obtain x. And we can also perform latent inference. We can discover latent representations by taking an x, passing it into the inverse of f, and that gives us a z. Now, the challenges of building normalizing flow models, as I said, is that we have to define these complex transformations that are both expressive and invertible, and the determinant is tractable, right? And the main challenge is to compute determinants of n by n Jacobians. Normally, this is an operation, by the way, that takes n cubed time, right? So taking the determinant of a matrix is n cubed time. And you can think of the challenge here. You can think of, so when we design normalizing flows, the main challenge we're trying to solve is to compute functions f for which the determinant can be computed more efficiently than in n cubed time, right? And so I guess one strategy to make things more explicit, one possible strategy that could be used is to use this observation that we need an efficient way of computing this operation. We can use this as the guiding principle for defining normalizing flow models. I haven't mentioned this explicitly, but this is essentially what we're trying to solve. And our idea of using simple mappings, the composition of simple mappings, is thought of being one way in which we ensure that this determinant is tractable. If each mapping is simple, then things are going to be invertible. But more generally, there could be other ways of ensuring that we have an invertible Jacobian. In particular, if that Jacobian happened to be triangular, that could also that would also give us an efficient method, right? Because we know that for a triangular matrix, the determinant is simply the product of the diagonal entries, right? It's the product of the diagonal entries, which means we can do this in big O of n. And that's going to be a completely different way, and also, in some sense, a more practical way of designing invertible transformations that we're going to look at in the next lecture. So I guess in this lecture, we gave motivation for normalizing flows. We defined change of variables, which we need to define flows. And then we defined what a flow is and gave one simple example. In the next lecture, we're going to look at some non-toy examples of normalizing flows, and their design will be based on the strategy of maintaining a triangular Jacobian matrix. And these models, these non-toy models, will be useful directly over interesting types of data like images or audio, and that's what we're going to see next.